Hello everyone, welcome to GRAMOLY's YouTube channel. Today I am taking a lecture on mathematical induction. First I will try to explain what mathematical induction by analogy. Then we will try to move to the formal definition. It is not formal, but a commonly accepted one. So first, as you can see, there is a set of dominoes here. And as you can see, they are falling one after another. So dominoes. What do you see in this dominoes? That one domino falls, another falls, and in this way a continuous wave of dominoes falls. So, what is the relation between this and mathematical induction? So essentially, mathematical induction is a method of proof, and I can say that it is a wave-like structure. So first, I will say that the first is the P1. And what is P1? This I will tell you now. So mathematical induction is a wave of proofs. Suppose we have an infinite number of propositions. Infinite means infinite propositions are there. And proposition. What is proposition? Proposition means a statement which has to be proved. And it is numbered like P1, P2 and P3 until infinity. And if I can prove two things, that P1 is true, and by P1 is true I mean that I strike the first domino and it falls. And the correctness of one proposition implies the next one to be true. That it means that if the previous domino falls, the next one will fall too. And if I am able to prove that first one will fall and if one domino falls, then the next one will fall too, then that automatically means that all dominoes will fall. And that means P1 falls, which means P1 is proved, then P2 is proved, and if it is proved for a k domino, then it means that the k plus 1 proposition is true. Then that means that P of n is always true for any n. So this is the basic principle underlying mathematical induction. So you have to keep it in mind, but you will get more familiar with it once I start out the problems. And I am starting now, but before that I would like to give you a reminder. Do remember this before trying out the problems. To try the problem before seeing the solution. I will present the solution here, but to make the most out of the problems, you have to try it before seeing the solution. And so make the best out of you can from this problem. So first we will start from a basic, very illustrative problem, which means that this will make you understand a lot about mathematical induction, what it is. So if we cut 1 by 1 square from a 16 by 16 square, so first you will see that this is a 1 by 1 square, a small square, 1 by 1 square, and there is a 16 by 16 grid. And if I cut 1 from the corner, yes, there should be a corner here, then prove that we can cut it out into trominos. So here you can see a tromino is a L-shaped structure of 1 by 1 squares, and this L-shaped structure is what we call a tromino. And for your help, I have kept here a 16 by 16 grid, and here we can cut it a 1 by 1 square. And after cutting it, what we have to prove is that we can divide this 16 by 16 square into piece of trominos. But we will start it like this. First we will see. First, I will actually try to help you with that. What we have to do? We have to actually try to set up with the most basic case. And so the most basic case would be something like a 2 by 2 domino, or 2 by 2 square. And this 2 by 2 square, suppose let's cut a 1 by 1 square from it. And as you can see, it's obvious that there is a tromino and it will be formed. And now, it seems that this is what we call the base case. Base case means the simplest case which we can prove. Or it might be self-evident in some cases. So now let's step up the game. This seems to be very simple, and anyone can do it just by seeing. Now let's set up the game. So we have now a 4 by 4 domino. This is 4 by 4 domino, and I have tried to cut. I cutted a 1 by 1 square from this, and you now have to prove that how can we cut into trominos. So first we will see that we can divide it into 4 2 by 2 4 2 by 2 grids. And we observe, we have already solved it for 2 by 2. Does it lead us somewhere? Yes. By how? What happens here actually? So see, when I cut it from here, I can now get at least 5 dominoes by seeing like this. See, first there is a this L-shaped domino, this L-shaped domino, and there is also this shape. So these are the structures formed by cutting, and we will get this like this shape from the 4 by from the 2 by 2 one. And by cutting it dice, we solved the problem for the 4 by 4 one. But does this tell us something more? What is the something more? See, first I started from 2 by 2, then I moved to 4 by 4. As you can see, I am trying to take it from the powers of 2. Now I will move from 4 by 4 to 8 by 8. From 8 by 8, you can see that it can be similarly done into 4 by 4 squares, and we can also try the previous method and cut into dominoes. So it means that we are very close to proving. And proceeding similarly, we see that the 16 by 16, 2 can be cut into dominoes. Here we are done. You might think that it is a little bit of non-rigorous solution since we haven't used much mathematics here. But I will leave this up to you after some time when you get the required one, required experience. But this was a very illustrative proof since I was able to explain that how we can move from base case to the larger one in mathematical induction. So here it will be done. Here this is done, this problem. And now we will be starting with the second problem. But before the second one, I would like to say that there are a lot of elementary identity problems in induction. And in high school, this is usually taught what induction is. But actually, this is not the goal of induction, since there is much more access to it, which you can see now after this problem. So here we are given a simple identity, not be simple since it might be surprising, that 1 cube plus 2 cube till n cube summation is equal to n square, n plus 1 square by 4. We have to prove this. Essentially, there is another way of proving by backward summation, but for now, since we are doing the topic of induction, I will do this method. So first, what you have to do? But as I said first, you have to first prove that the P1 will fall, the first domino will fall. So that means I will try to prove it for a very simple case. And what is the simplest case? Here, that would be 1. So let us try to prove it for 1. So putting in n equal to 1, we get this side equal to 1, which means that the LHS equal to 1. And now let's put it here. Here you can see, checking for n equal to 1, we get this LHS equal to 1, obviously, and RHS equal to 1 into 1 by 2. The 2 cancel out and we get 1. So this tells us that P1 is true. Now we can move forward by assuming Pk to be true for some k belongs to n. Then we assume that there exists some k which is true for this statement. And now we will try to move to the next statement, which is the k plus 1 domino. And if we prove that the k plus 1 domino will fall, then we can say that this statement is true. Let us see how. So first I will do this like Pk is equal to this. I will rewrite the statement in form of k. Then I will try to manipulate it to get the k plus 1 statement true. So first I will add k plus 1 cube to the both sides. Yes, I will add them. Then I will try to get into a form of k plus 1. Then let us see. I add this. Now I can actually simplify it to like this. So I get Pk plus 1 is equal to k plus 1 square, k square plus 4k. This is simplification. I am taking out common. Now we get this form which was expected. Since you know that the statement was like this, and if I replace n with k plus 1, then I get this statement. So this implies that this statement was true. The k plus 1 will fall. So this means that this was the form which was expected. And so we are done here. On this 1 by PMI, this statement is true for all n. So this was an elementary identity problem. So identity problem, you would see I am actually giving some problems here from identity 1, and these are prove 1 plus, this is a very simple one. I should have usually taken this one, but this is a classic one which every beginner tries to prove with the first problem in induction. And these are another one. There are some problems, and This is the sum of the geometric series one, and this one is a popular one. And this problem is also famous. So these are some famous elementary identity problems. So these are usually the best problem for beginners, but as I said, this is not purely what induction is. We will actually see the application of induction in many fields of mathematics. So here are some resources which you can try out surely, and I have actually taken some problems for them too, and I have taken some from mathematical circles. You can actually see out and try out the first solution, which is given in the form of dialogue in the big reading of mathematical circles, chapter 9. And in brilliant organization, brilliant website, there is some summation problems. You can also try it there. And flawed induction proof. I wish to cover that in this video, but due to some time constraints, I will not be able to do so. But you can surely check it out, since this will actually help you to get out of some common pitfalls which you can avoid now. So after some basic familiarity, we will move to some other parts of induction. There are some variants of induction which I will be discussing. The idea is not to get a comprehensive one, not to cover all the variants. Variants actually stem out from one variant, but we have to actually give some. I am trying to give some basic introduction. So that's why this doesn't aim to be comprehensive. So let us start with problem 3, which is let an. This bracket actually means to denote a sequence of natural numbers such that a1 equal to 5, a2 equal to 13, an plus, this is a recursive relation, and for all natural numbers n, prove that an is equal to 3n plus 2 raised to n for all natural n. So those of you who are not familiar with recursion, I will tell you that recursion is a method in which we express the sequence, which we express a term of the sequence in terms of the previous one. As you can see, an plus 2 is expressed in terms of the an plus 1 term, so n plus 1 term and n term. So that is a recursive relation. And this one, as you can see, is purely in form of n. And this is actually usually the solution to a recursion. Yes, you can do some reading for recursion. So let's do it. First, I will actually try to motivate you that how we move to this solution, and then I will present the solution. And the aim of this walkthrough motivation is to actually lead you towards the solution, so that you can actually try to solve it yourself. So walkthrough first let us check whether the base case is true or not. This is something which should always be done, whether the induction is self-evident or not. So first we will try out for the base which is true, and then we will do the generalized statement. Since after base case we move from the key to the key plus 1, or say we generalize the statement for every n, and if it's true, then we are done. So first we will start on this. I am starting on to the solution. Solution is like this. First we will do the a1. What is a1? See, a1 is equal to 3n plus 1, and that is 5, right? You can see here, I just put it 1 here. And a2 is equal to 9 plus 4 plus 13. So I have got two base cases which are correct. So it means that this statement is at least true for our two numbers. And now I am going to do the inductive step, which is to assume ak is equal to 3k plus 2 raised to k, and ak plus 1 is equal to 3k plus 1 plus 2k plus 1. This might be something which you might feel as new, that I took two base cases. Yes, it's absolutely possible to take two base cases and to prove it. So let's try to put them in the relation, the recursive relation. So let's see. an plus 2 is equal to 5an plus 1 minus 6an, right? Now I will do it like this. I will put them inside. Now as you can see, I now simplified it and I will reach this form. And after reaching this form, as you can see, I moved from those two base cases to this case. So that means I am done here. And this problem is solved. And as I earlier said, there are some variants of induction which are very important to discuss. So I will only discuss strong induction here in this case, and before moving on to some problems. And as we saw in induction earlier, that the main induction, it's not main, it's actually a subset of the strong induction, that we usually choose the base point to be 1. but we can choose any point, we can choose any other base as well. This is something to be realized. As you saw that this time I choose two bases, but it's absolutely possible to choose any other case as well. But we will see the condition what is here. We can choose any number k0 as the starting point. This is for strong induction. And then proving from k0 to all k. This is a way. And assume that p of or there is another way to assume that p of m is true for all m which is less than k plus 1. Then moving forward. And these both approaches are equivalent, as you can see. If you try to reason it out, then you can see why these are equivalent. So strong induction is the popular name. Is the popular name of this variant, and is usually mainly the main case. But the base induction, which I taught first, is the more popular one too. But actually, strong induction is the superset of that induction. So this one is a superior one. So now we can confidently move on to some problems. Although before moving on to problems, I will actually say that these problems are not entirely of induction. You will require some type of ingenuity while solving it, and we can only do this by practicing a lot. So don't get too much surprised while doing this, and we will try them out, and then try some similar ones too. And I have given some practice problems too in this handout tab thing. And as I said earlier, in these problems I will try to keep a motivation section so you can try to make out the solution by yourself and why that approach was used, which probably will help you. Since I can actually say that this one will actually help you all. So it's problem 4 now. This one is another identity type problem. Let n be any natural number and prove the identity. The identity says that the summation of this term, as you can see, k2 upon k raised to 4 plus k square plus 1, this term, the summation of n terms from k equal to 1 to k equal to n, these terms is equal to this right hand side here, and right hand side, as you can see here, and this term is a very important term here, and as you will see soon. So now I am starting. First time I will try to help you by motivating you what this is, and yes, first notice this term. What this term is? This term is a very familiar term, and as you can see why. If you did the exercise which I told you above, or if you knew it already, then that would be the sum of all natural numbers till k. Yes, and then I will write this. Yes, I said that correlated with the identity. And if you know that if I am summing from 1 to n, right? Summing from 1 to n, and if I have to sum from n plus 1, and if I subtract them, then what will I get? I will get the term. And if I think it like this, that if I add all the summations, and if I subtract the larger one from the smaller one, the immediate one, then I will get a term. So I will say that try to find the difference of two consecutive sums and realize what it actually means. This, I am now moving on to the solution. Hopefully you will have tried enough, and replacing sum of k terms with n into n plus 1 by 2, the identity, we get this form of equation. Yes, we can try to express it as a function of n. You can actually say, just for some notation format, I have written as f of n is equal to n into n plus 1 by 2 into n square plus n plus 1 as a function of n. And let us assume that it is true for some k. Then what will be the k plus 1 sum? So let us see what happens here. This is f of k plus 1, right? F of k plus 1. Just written in k plus 1. And the difference should be the k plus 1 term. So you will now realize what actually happens here. That if I sum here from k plus 1, I will sum here till k plus 1, and sum this from k term till k term, and if I make the difference, if I take the difference between those two terms, I will have to get the k plus 1 term here, and which is what we are trying to prove here. So now let's go. See, first I wrote the sum like this. See, I wrote it in this form. As I told you earlier, I go like this, and I wrote it for k term, and I will subtract it. And after subtracting, I should get the term. not this sum. See, I tried to simplify it by taking k plus 1 by 2 common, and then after some manipulation, this is sometimes hard to see, but after enough practice, we can do this. That cube and k plus 1, this sum, and we can now go to this one. See, this is what was expected. Why? Since you see that k was like this, and if there was k plus 1, so the k plus 1 term would be like this, right? K plus 1, k plus 1 raised to 4, and k plus 1 raised to square plus 1. So it means that our induction was correct here. Why? Since after subtracting the sums, I got the right term, which was expected. So here we have done by PMI. And for a twist, there's also a nice solution by telescoping series method or say partial fractions. And then my challenge is to find it and do it by telescoping sums, and it might be easier for those of you who are experienced with partial fractions. So I will now start out with the problem file, and this is the prove the inequality for n greater than 1. Now we are going on to some new part, which is using the application of induction in other parts. So now prove the inequality for n greater than 1, and I am now putting out the inequality in front of you. This is 1 plus 1 by 2 square plus 2 summation till 1 over n square, and I have to prove that this is greater than 3n over 2n plus 1. And if I will now try to give you motivation about it first, but first look at the problem and try to try it. So it might be simpler for many of you. So first observe by what the term does both side increases for the n term. That means when I add an n plus 1 term or an n minus 1 to n term, you will now see what the difference is, by what term it is increasing in both sides. First find the difference. You might have seen the difference method is very useful. The method of checking out the difference is very useful. And try to see which grows faster. I am not saying. So taking differences we get. If n minus term was there and LHS increases by 1 over n square and RHS is given by, see, if there was a 1 minus n minus 1 square term here, and for if I add something, then I will get 1 over n square. It increases by 1 over n square, right? Hopefully it is clear to you. And then what we will do here, that there was a sum, and this one will actually take the difference, right? Since the RHS, for the RHS this is here, and to find it how much it increased, we will do it like this. We will take out the difference, right? And 3 over 4n square minus 1. So this was actually the way of actually thinking about this problem. Then we can move to a solution. So first I am saying that proof. If I prove that LHS grows faster for n greater than 1, then I am done. Since if I prove that LHS grows faster than RHS, then I can say that this is always larger. Since as n grows larger and larger, this statement will become more true. So let's go forward. Here's where induction coming. Assume for some k greater than 1, this is true. I subtracted to get the difference by which it was growing. And yes, I got this one. And we can even verify this by using a base case, putting in a base case and then proceeding forward. Yes, we can actually put out some number and we can see that why this is true. And this is clearly true, as you can see. Cross multiplying both sides, since this k square term would evidently be lesser for all positive integers, 4k square. This will be actually more larger. So in bold it means that this fraction will be lesser. I am right here. Cross multiplying both sides with no fear of signs, or else you can also cross multiply with no fears of sign. There is no fear of sign since they all are positive integers. Now we can move it like this. 4k square minus 1 is greater than 3k square. Then I can subtract this to get k square greater than 1 and k square greater than 1. This is a true statement. Why? Why is k square greater than 1? Since k is a positive integer, so it has to be greater than 1. And according to the original condition of the inequality, n should be greater than 1. This statement is no doubt true. And now we can forward that since k plus 1 square, 2 would have to be strictly greater than 1. If k is greater than 1, then k plus 1 will always be greater than 1. So it is true till here. So now we can reconstruct the inequality. This seems some This is not too motivating stuff like this, but we can actually go backward like this. We express this in terms of this, right? And we write it, and then we move this term towards here, and after that we get this form, and from this form, the k term, I have proved that the k plus 1 will be also greater than this one. So this automatically means that the inequality is larger. So this statement completes the induction, and hence to prove that LHS grows faster. To those of you who might have not understood this properly, you have to actually think slowly. Why the faster growing rate means that the LHS is greater than RHS. So think a bit about the difference. Why the difference caused the inequality, and why proving that the k plus 1 difference, as I said, proved that this inequality was greater, LHS was greater. Even if you think of it, I think you will get the answer why this proved the inequality. Hopefully that was clear. And we can say that by PMI we have proved this. And now I will move on to P6, the problem 6. Prove that for all n greater than 4, it is possible to dissect any non-equilateral triangle into an isosceles triangle. So it means that we have to prove that there is a non-equilateral triangle, any scalene triangle or any isosceles triangle will work, and I have to prove that any n greater than 4, I have to prove that I can dissect this into an isosceles triangle like this. Actually, it's not a proper figure. You will see now. I have to prove that I can dissect it into any n number of isosceles triangles. So let's see this. Motivation. So first I will say that there is a. First I will actually try to prove this for a general general way. I will actually try to get in scalene triangle, and we will do it like this for a right triangle. This is an obvious geometric property, but those of you which are not familiar with too much geometry here, I will actually try to prove it here. That we have this one, and if I make a perpendicular bisector here, not a bisector but a perpendicular, then I can make it like this. This y, yes, this y. This y angle would be equal and xx would be equal. So I have rightly got two isosceles triangle here, and these two isosceles triangle I have got. And if I have any triangle, then I can try to divide it into two right triangle. And if I divide that triangle into two right triangle, then I can divide the right triangles into isosceles triangles. So see, first I am actually telling you how we can divide a right triangle into two isosceles triangle. And then I am saying that we can divide any non-equilateral triangle into two right triangles. And if I am able to divide two right triangles, then I will divide them into isosceles triangles like the figure above. You cannot see it. You cannot see it clearly. And this was actually a very important step. That's why I kept it here. And now let's prove it. Build induction. So we saw a base case above, right? And we will try to prove it in inductive way. Suppose all non-equilateral triangles can be divided into m isosceles triangles for some m which are greater than 4. Give strong induction here. For some m greater than 4, right? And suppose we have a non-equilateral triangle ABC with shortest side AB. So see, first I actually told you by assuming that we have an all non-equilateral triangles can be divided into m isosceles triangles for which m is greater than 4. And if I have a non-equilateral triangle ABC with shortest side AB, and shortest side has to exist, which is obvious, and we take a point D on BC such that BD equal to AB. See, I have this triangle which is non-equilateral according to the position, and I try to find a point D here such that BD equal to AB. So hopefully this has been clear. Why? Why this has to be true? Since AB is the shortest side, I can take any length equal to AB in the BC. Since AB is the shortest side, it might not be clear. So since AB is the shortest side, I can take out a length BD on BC, since that has to be true. Then we see that ADC is not equilateral. Why ADC is not equilateral? Since I assumed that the triangle was non-equilateral and AB was the shortest side, then this C would have been to the largest angle, and if it is not equilateral, then you will see that C is the largest and it cannot be 60 since ABC is not an equilateral triangle. Now dividing ABC into m isotriangles, I will divide this into n isotriangles. See, I told you earlier that I assume that I can divide any non-equilateral triangle into m isotriangles, right? I divided it like this, then I will divide into m isosceles triangles. And if I am able to divide this m isosceles by the induction hypothesis, then see, I have successfully divided ABC into m plus 1 isosceles triangle. Since ABD is an isosceles triangle, this proof sometimes strikes, so you can actually reverse the video a little bit why this was true. And we have successfully divided ABC into m plus 1 triangles, and yes, we have proved it. Now I will move to the problem 7, which is let A be a real number such that sin A plus cos A is a rational number. Prove that sin raised to Na plus cos raised to Na is a rational number for all n which are natural numbers. See, this is a problem which requires some trigonometry, and I will actually say more to the trig basics. So first I will try to motivate by saying for the base case, saying about the last case. So yes, get back to trig basics and remember sin square A plus cos square A equal to 1. Very simple, but I am not going to provide the proof here, which is a simple application of Pythagoras. We now have two base cases which we can use to proceed further. See, what our base cases? We are given that sin A plus cos A is a rational number, right? And I know that sin square plus cos square A is also a rational number, which is 1. So I now have two cases and I can use them to proceed further. Let us see how. Using the fact that sin A plus cos A square is equal to 1 plus 2 sin A cos A. See, since sin square A plus cos square A equal to 1 and 2 sin A cos A, which I am writing here, and now I will try to prove that this is a rational number. See, since it is a rational number, we knew it, and if a square of a rational number is also a rational number, and this means that this side is rational too, and 1 is rational and 2 is rational. This means that sin A cos A is also rational. So I have proved that sin A plus cos A and sin A multiplied by cos A both are rational. And if I prove this, and assuming that sin raised to Na plus cos raised to Na is rational, we will go on to prove this. As you can see, sin raised to n plus 1a plus cos raised to n plus 1a is rational, then we will be done. So this is what we are trying to prove. And these are the base cases which we have go. And if I am successfully able to move till here, then I will be done. So see, you can write it like this. This might be for some people this might be difficult to think, but we will actually try some there sin plus cos n appear, and we get these terms too, and we know that we will just subtract these terms, right? And we know like this is a rational number, this is a rational number, then the product too has to be rational, and this product is also rational as I proved above. But what about these terms? We don't know whether they are rational or not. But one thing we know, that we can express them in forms of product like this, just like I did here, and we will do here that till reaches it 1, till it reaches till the case where n equal to 1, and I can factorize it into many pieces, and we can go on continuously. So what actually means that sin raised to n minus a plus cos raised to n minus a is also rational. So what this implies? This implies that sin raised to Na plus cos raised to Na is also rational. And this actually concludes the proof, and you can see that the product of rational is rational And since we proved that the product is recessional, we can express the bracket 2. And by PMI, the principle of mathematical induction, we are done here. This one was a nice one in algebraic terms, little bit. So let's move on to the last problem. This is going to be your last problem before I present to you the practice set. Some problems, not too much. I am playing the color country game against Bob. I am playing the color country game. So those of you who might have heard about the maps one, this will be a simple one. 4-color game. The 4-color, not game, but 4-color theorem, which seems try to draw the map. If we draw a map, and you have to color it in such a way that the adjacent countries don't have the same color, then I have to compulsorily use 4-color. This one is what this problem is based on. I am playing the color country game against Bob. We take turns. Obviously there might be turns. And on my turn, I draw in a country. On Bob's turn, he chooses any color for the country. But he must make sure that he never colors adjacent countries the same color. What I explained ago. Is it possible for me to force Bob to use more than 4 colors? This is the original one. I said this one. Since in the solution, we actually prove it generally for n colors. So I did this. Or more generally, more than n colors. So it is asking, is it possible for me to force Bob to use more than 4 colors? Or more generally, n colors? So first time, I am going to try to motivate you by explaining you how the game works. And I will now show the strategy. What makes us win here? What will make me win here? This doesn't seem like naturally a problem to apply induction on, but suppose we try to generalize it, then what happens? See, my turn n equal to 1. N equal to 1 by me, this is the color, and I am now drawing a country. It doesn't look like country, but just a blob. And in Bob's turn, he colors it, right? Now this seems too simple, but let us try to force him to use the second color. How will I force him? Actually, there is a way just to draw like this. But in order to give you a view of what my advanced strategy would be, I will become smart and draw this. This will actually force Bob to use the second color. And this country's border, as you can see, is completely engulfed by the new country. So there will be wars here. Just joking. And Bob's turn. Now he will be used to force another color, or he will lose the game. Right? Now Bob will use this blue color. But you might have guessed now, what is my strategy? My strategy is to make something like this. To make Bob use n colors around, and then I will make a country which covers the whole. I will make a country which covers the whole part. And if that covers the whole part, then that means that Bob will be forced to use the n plus 1 color. So see, to make him use n colors on countries which are disconnected, by disconnected means that they are all have the color in exterior, and then make a large country engulfing them all. So you will actually now ask me, what if Bob tries to choose the same color when we are disconnected countries? The solution is that I will actually make Bob use first n color, use one of the n colors in one blob of country. By blob I mean some group of country, and then I will just color one, and he will color one, and then I will try to make another blob farther away, and then I will force Bob to use the next color, which is the second one or the next color in the exterior in that blob. And in this way, I will try to force Bob to use all of the colors, n colors, in exterior, and then I will engulf them all by drawing out a larger one for the n plus 1 color to force it. So we have already proved for the base case in motivation. What was the base case? That to force him use the 2 colors, right? So let us just assume that we can force Bob to use n colors. Then we will proceed as above to make him use n colors in exterior, and thus we will make him use the n plus 1 color. So this was something like the proof was already in the motivation. So this problem is now concluded since we can force Bob to use the n plus 1 color, and now we can specialize it for 4 colors. And now we have done. Since I proved for the general case in the motivation and now specializing it, I have done it for 4 colors run through. And for problems, I have given just a small problem set here. There are some contest problems above, and in these problems too, I will not give the source out now, but if you want, I will later put out a PDF or something like that for the sources. So here first is a problem, the Tower of Hanoi. This is a popular problem in computer science for algorithmic analysis. This Tower of Hanoi, and I have given out a link here for you. You can actually try the Tower of Hanoi out there. You can actually play it a little bit to get familiarized at how this game works. And I will written the rules here for you. These rules are important, but after playing a bit, you will eventually get familiarized with this one. I will not explain since that would be the purpose. And this one is a geometric problem here, nice problem. And another inequality one. This is a contest problem, and it is from a famous teacher also. And prove that for all integer n greater than 1, this is also an inequality problem. Sorry, not inequality, but it is solvable. We have to prove this. And h9. This is a contest problem, the popular contest, and we have to actually use some number theory in it. And this one is an old problem, little bit popular inequality one. You can see that use induction here, and I am sending you these problems. You can try it out after learning a little bit prerequisite backgrounds. So I hope so that you understood what I presented here in the video. And if you like the video, subscribe to GRAMOLY and share it. Thanks for watching.